Continuing on with our investigation into the motor vessel Dali Collision into the Francis Scott Key Bridge back in 2024, the National Transportation Safety Board has given us what we think might be some good root cause analysis. And we've also got a couple of new security camera videos that you've never seen before that show different angles of the Dali colliding with the Francis Scott Key Bridge. We are going to show you what the NTSB found as the possible root cause for what was wrong with the Dali ship. So this is why I think they tried forcing it in there. This is the crux of the problem right here. Now, before I show you the root cause and how it was able to affect the Dali and shut the entire ship down, I want to show you these other video angles from these security cameras of the incident that you might not have seen before. So check these out. So this is a view from the industrial processing facility. It looks to be about southeast of the bridge. And there's Dali arriving on March 23rd. So just a few days before the incident, and it passed through just fine. Now on the night of the accident, look at this. This is normal speed of Dali entering the upper left screen taken from the southeast. So now I'm going to speed it up and you can see there she is floating across there. And somewhere around here, she's going to start to lose her power. So here we go. Watch the ship very carefully. You'll see it. Boom, right there. It just went dark at this point. So this is the very first time that it loses power before hitting the bridge. Now for the next minute or so, I'll speed it up here for you, 8x, so you can see she's floating along in the dark. And then any second now, after about a 60-second blackout, you will see they finally get the lights back on right around there. See that? So the lights are back on now, and they're probably giving a sigh of relief, thinking everything's okay. But then it's going to happen again. Now I've sped it up again 8x, and there's only about 2 minutes before the collision again into the Francis Scott Key Bridge. And so now you're going to see the power go off again a second time. And that should happen sometime around here. There it goes, see? It just dimmed out. And so now there's roughly a minute and a half to go before it crashes into the bridge. You can see the traffic on the bridge is now slowing down, and that's one of the last vehicles to cross over the bridge. Now you'll see the lights come back on right there. And remember, they still don't have the engine turned on because there was so many things to do in those few seconds, they just didn't get around to it yet. And then as I speed it up a little bit, look at these last two cars. Looks like they're going over, unless that's one truck. I believe that might be a truck. That's the last vehicle to cross over this bridge before it collapses. And now I'm going to zoom way in here for you so you can see just the Dali and the bridge. And you can see it's going to collapse any second right there. So there it comes down right over the top of the Dali, and the Dali is staying still. And you can see all of the power slowly going out on the bridge lights. And then on this third security camera, I've sped it up 20x for you. This is from a private residence on Dundalk, and you can see Dali going from left to right across the screen there. And so as she gets closer and closer, you're going to see the power go out sometime around here. Maybe it's in a few more seconds. Okay, I zoomed in on it here for you. So there goes the power the first time. The lights come back on, and then there goes the power again. The lights come back on, but there's no time for them to really react because they're just too close to the pillar. So now here we are at real time. You can see Dali is still moving, and it's about to crash into it. And you should see it collapsing any second now. And it should be coming up right there, yep. So you can barely see it. It was captured off of the left part of the screen. Now you're going to love this animation I'm going to show you here that shows exactly how this failure mode happened. And then I'm going to show you a failure mode that you've probably seen very similar in your own house. The motor vessel Dali's electrical system distributes the power and control signals throughout the entire ship. And it does it through these blocks that you see right here on the screen with wires that connect into these terminal blocks. The wires on the Dali were terminated with these metal sleeves called ferrules that allowed for easier assembly into the terminal blocks. So for example, here's a sample piece of the wire that they took from that same terminal block, and there's your ferrule, your metal ferrule, and there's the blue plastic cap that goes over it. And what a metal ferrule is it's basically a metal tube that surrounds your stranded wires that are all twisted up inside there, because it's a lot easier to stick a solid metal tube into the connection point on your terminal block than it is to try to insert these twisted wires here. And then you can see 1, 2, 3, 4, 5 points on here where the ferrule is crimped onto your wires. Okay, And each wire and ferrule has its own labeling band, as you can see here in the diagram. Okay, so here you can see 4 terminal blocks on the Dali that have their wires connected in there. To assemble the wires into the terminal block, you have to use a tool inserted into a side port that opens the spring clamp, which allows the wire's ferrule to slide into place through that rectangular eye you see on the top of it. When you pull the tool back out, this closes the spring clamp, securing the ferrule firmly against the terminal block's internal conductor bar. Labeling bands identify the wires and are typically positioned on the wire insulation, as you can see further back. But guess what? Many of the labeling bands on the Dali wires were placed partially on the ferrules, which actually increases the ferrule's overall circumference. Because of this error during construction, some of the ferrules could not be fully inserted into the terminal blocks, including this ferrule here on wire 1 from terminal block 381. Let's see how this error with the thicker plastic affected it. So on that wire, the labeling band prevented full insertion of the ferrule so that the spring clamp actually gripped only the ferrule's tip, resulting in an inadequate connection. Okay, so I made this slide here to show you. I took both of those images and put them side by side to show you. So here's a normal wire, and there's the beginning of your ferrule with the purple plastic over it, and there's your ferrule. So you'll notice how the ferrule goes all the way through this hole in the clip, and it extends all the way in. And then when you pull the tool out, the tension from this clip here holds everything together. It holds it against the side here. So that's how it makes its contact. But in the case where they put the label too close, you can see what happened. It increased their circumference. So now the purple plastic part of the ferrule cannot slide down into this port opening. So you can't get the connection. And so this is the result. This is what happens. You don't get the ferrule going all the way down and all the way through. So you get enough vibration and some heavy seas over the years, and it's enough to start wiggling this thing loose. The next thing you know, it pops up a little bit, and you have a gap, and then you can end up with arcing. So due to this loose, unstable connection, over time, the ferrule on wire 1 pulled out of the spring clamp to rest on top of the spring clamp face, resulting in a very precarious electrical connection. So when an arcing gap occurred between the ferrule and the spring clamp face, the electrical circuit was then interrupted, leading to the blackout of the Dali. So I've gotten called by numerous friends over the years because their outlet was working 1 minute and then not the next minute. So like the lamp is not working now, but it was working last night. So I have made this repair a number of times over the years while remodeling my foreclosure properties. And so this is what happens here. Here I'm showing you on a switch. So to me, the gold standard is you wrap the wire around a screw and tighten it down. That's how you're supposed to wire an outlet or a switch. Now, what your builder does, because a lot of builders are cheap here, and they use cheapy electrical contractors that don't know what they're doing, what these guys do is many of the outlets and switches have these little holes on the back that we call them backstabbing holes. Because they're too lazy to take the time to wrap the wire around the screw, what they'll do is they'll take the wire here and they'll stick it into the back like this. And you can see here, let me see if I can pull it back out. See how it came out that easy? That means we didn't get a very good connection there. But yet, I can't pull this off of the screw. So you have a much more reliable connection this way. And so this causes arcing because it's not making a good connection. And that's what we saw here on the Dali. So you might have heard that the Dali had lost power while sitting at the dock the previous day. And some people thought, well, maybe that's related. It really wasn't, but this is what happened there. So here's your diesel generator number 2. This is what was operating at the time. So during maintenance at the port, one of the crew members had accidentally closed the exhaust damper on the scrubber here. So that means that now it can't exhaust out to the outside. So that caused this generator here to stall. So now you don't have any more 6600 volts, and then you don't have any more 4400 volts. So they lost power to the entire ship. And so while this was spooling down, now you're looking here at diesel generator number 3 is up and running. But guess what? It's running low on pressure there. And so DGR3 opened up, its fuse opened up. So now it's offline. So now we have another complete blackout on the ship again. And also during this time, they were now getting the power through this path here, through HR2 and LR2 instead of through HR1 and LR1. And then, of course, they finally reopened the damper here and got diesel generator number 2 running, and then everything was fine. But on the evening that Dali left the dock, what happened here? So now on the night of the cruise, here's what happened: is they're basically 4 minutes away from the bridge. It's 1:25 a.m. And guess what happens, folks? They get an LR1 here trip. So this is the VCB. This right here is a vacuum circuit breaker on this leg of voltage here. And so what happens is these generators here give us the 6600 volts on the high voltage bus. Then it steps down through TR1, which is a 15:1 ratio step-down transformer to get us to 440. So see, if you divide 440 into 6600, you get 15. So the windings here are set 15:1 ratio to drop it down to 440 volts. But this guy right here tripped. LR1 tripped, and they didn't know why at the time, why it was tripping. When this happened, this took out here the 3 steering gear pumps. So there's the first part of your problem with not being able to steer. Okay, so then all of a sudden, these 2 generators right here, 3 and 4, they were continued running, okay, and so they were actually still supplying power here to the high voltage bus, even though the low voltage bus down here was already down. But the fuel in these 2 eventually ran out because they weren't getting enough pressure now, and that they were just basically running off of the residual fuel. Okay, so then the emergency generator kicked in, so now they had at least power on the low voltage bus. And then about a minute later, you would start to see diesel generators 3 and 4 were starting to underperform because they had insufficient supply of fuel in them. So that was part of the problem. And so then on top of that, the power management system detected the underperformance and the frequency drop there. And so it automatically turned on diesel generator number 2, which had been sitting there in standby priority. And so now it was trying to supply power here to the high power bus. So now about a minute later, before the PMS system, that's the power management system, could get diesel generator 2 up and running and fully synchronized, that is when these 2 generators here finally had run out of steam and they had shut down. And so since he's not up and running and up to synchronization yet, and you can't turn him on, you now have no power to the entire ship. Everything shuts off here at this point. And by the way, when these shut off here, by the design of this ship, the HR1 and the LR1 both open. So that's why you lost power here to the low voltage bus as well. So now, once again, the entire ship has no power. And then several seconds later, finally, diesel generator 2 spins back up. You can see like this funny, strange domino effect going on here with I'm on, I'm off, I'm on, I'm off. And so that's what was happening here. It's just the timing just wasn't quite there for these generators, and then running out of fuel before the next one would come online. Okay, and so now the frustrating electrical dance continues, because now that we have generator 2 online and these 2 are kind of offline, they decided, since these are now popped open, LR1 and HR1, we're going to switch over to LR2 and HR2. So they closed these, which supposedly gives you power back now to both cabinets, to both power buses. So everything's back on again, the lights are back on. And because they were using this strange kind of flushing pump to get the fuel back into diesel generators 3 and 4, they had to send somebody all the way down several decks to go and manually restart this, because for whatever reason it wasn't set up to be automatic, which I guess many boats already have that set up to automatic. So that's something they're going to look into. But then, of course, what happened here was they were asked, well, did you restart the engine at this time? And they said, we just didn't have enough time to get it started. And then, of course, at 1:29:09, which was basically less than 2 minutes after the second power outage, is when the Dali struck Pier 17 on the Francis Scott Key Bridge, bringing the entire bridge down. So here's how they discovered the problem. So what happened was, when all of the engineers were in there testing and everything after the incident, so this is about a month later, all of a sudden LR1 popped open on them. And they had a blackout. So, oh, okay, this is a great chance to figure out what's going on. So they put these power analyzers here on the terminal blocks to try to get them across. As you can see, this is where they were put right here, to try to figure out what's going on with LR1, but they didn't find anything wrong with it. So here's what the LR1, the entire breaker panel and everything looks like inside there. Yeah, so here's the HR1. This is the vacuum circuit breaker right here for HR1. And then over here on the left is the LR1 breaker. So they were testing all of the wires leading to those. So it was sort of like finding a needle in a haystack. Okay, so here is what they found then. They noticed when they pulled out HR1 out of the rack, this is the under voltage release control circuit. So if it detects that there's no voltage coming into it, the circuit here, it will trigger this under voltage release, which will trigger HR1. So that's what this whole circuit is right here. And you can see this circuit is powered right here by 110 volts DC. There's one rail, there's the other rail. And so the voltage is supposed to come in, and it's supposed to come down here and go through this GPT-1 relay. This is a relay that's in the GPT-1 panel. And this relay right here, as you can see the 381 right there? That's that block number. Remember we said that's that block number, 381. Remember they pointed that out earlier? So that's the one that failed, and it's wire number 1. So what happens is if all of these relays don't stay closed, the voltage from here will not make it into the under voltage release relay. And all of this right here will just go 0, and that's what triggers the HR1 to fail. So we know that that failure was here, so that's how they narrowed it down. So there's an engineer holding the wire that was pulled out, wire 1, out of the terminal block 381. And so on Dali's DIN rack here, this is what it looks like. Here's all of these Wago terminal blocks here, one after another. And here it is, 381. So there's wire 3 on the left side, wire 1 on the right side. This was the culprit. And I wish they had gotten a better angle of this to be able to see side by side how it looks compared to all of these other ones. But it makes you wonder how many of them didn't make it there. And here's a couple of more pictures that they showed after they pulled that line out. So this goes into the terminal block 381, and there's your metal ferrule sticking out there. See, there it is. Then they decided to visit the sister ship to the Dali, which is the Cezanne, and I hope that's how they pronounce it. But here's its terminal block, and it looks, fairly much the same. So they wanted to see if it had any issues with its wires. And then the power management system looks like this in the control room. So when everything's up and running perfectly, this is what it should look like. And then when you have issues, this is what it would look like. As here you can see that diesel generator 1 is tripped, and then also HR1 is tripped, and of course diesel generator 3 is tripped also, and 4. So this here lets you know when a circuit breaker has tripped. Now, a good engineer will do what I always did as an electrical engineer at Motorola, and I used to tell all of my fellow engineers too, if you think you have the answer to a failure in a circuit, then you should be able to control it like a light switch. You should be able to turn it on and off like a light switch several times. You need to be able to duplicate it several times in the lab. So that's what they did here. Okay, so you might be asking, well, how would they find and test every single wire in here? Well, it doesn't make sense to try to test every wire. And not only that, if I start unplugging wires, I run the chance of really ruining a connection somewhere or really causing damage. So I'd rather not touch them. So what they do here is they use these thermal imaging cameras and they aim it there. And if there's any heat or any extra higher current going through or arcing, it'll show up here on the screen. A lot of us use devices like this when we're remodeling the houses to try to find air leaks and where the insulation is not making good coverage and the sun coming down like on the roof or on the walls, you'll find hot spots. Just like this. So this sort of shows you an example, like this would be the image you see on the screen. Then I would take this and you could superimpose it over the image of the rack to kind of show you where it would appear if you had a bad wire going on. And now it's time for the fun stuff, the Materials Science Laboratory. So here's what they did. They took the terminal block with them. This is the Wago. And I use some Wago connectors too. I use these Wago wiring nuts in residential electrical wiring, which is a great alternative to wiring nuts. They're lever nuts, actually, is what they call them. But here you can see the terminal block, and there's the conductor bar. They then pull the bar out, so there it is, and they're inspecting it. Everything looks fine. I don't see anything wrong with the conductor bar. It looks perfectly normal to me. And this is what 4 of these Wago terminal blocks look like, snapped together. Now here's the close-ups of the wiring. So here's where they had the labeling band over the blue plastic part of the ferrule, and then there's your metal ferrule sticking out. And then when they zoom in on the ferrule and look, this is what it should look like, except for the labeling band being this close. But do you see how much diameter that labeling band adds to the ferrule. That's why it wouldn't fit into the hole into the terminal. This is what it's supposed to look like here. But anyway, on your ferrule, it's supposed to have these crimps, and then there's your wire strands inside. And then once it's been inserted into one of these terminal blocks, over the years, you'll see it'll leave this indentation. So that's how you know there's your first mark there. It should leave a single straight gouge there, and then possibly these other 2 points of connection here. That's how you know it had good connection. Okay, and so when you go to slip a wire in, remember the wire is going to come in through here, and it's going to go into this metal cage. But first they have to stick a tool down this side, which wedges against the clip here, and you'll see it right there. See, here's the tool in the next picture. So the tool comes in and it pushes the clip over to the left. So why do you want to do that? Because there's a rectangular hole in here. And once you push it over to the left, the wire comes down and goes through that rectangular hole and then into the cage here. And that's how you make your connection. Then you pull the tool out, and then after that, the clamp moves back towards the right and tightens up against the metal ferrule once it's in there. Yeah, so here's a better shot of where that port was, that connection port 381, see? And you still really can't tell from the outside that there's anything wrong with it. That's the thing. So here's the edge-on view look of the connection point 1 there. So now they're looking straight down the hole into this. Remember, this is the bad one. This is where wire 1 was. So you're looking straight down in there. There's your spring clamp, right? And you notice how you have that arc? There should not be an arcing mark here on top of the spring clamp. Why? Because the wire is supposed to have gotten all the way down the channel there into the cage. It shouldn't be popping back up and arcing against the top of the spring clamp. That was the problem there. See, here's on a good one right next to it. So connection point 3 running the other side of the exact same Wago connector. Look, see here? His is nice and clean. He doesn't have that arcing mark there on the top. And here's something else they noticed too. So you see here's the shell of the terminal block right here. And this is the bad side. You see what's wrong here? If you look real close, see that little mark in there? So they made a zoom in on it. They looked at it right up here. And a couple of things that you can see here. You can see that scratch mark. So I don't know if that was caused by the arcing or not. And I'm telling you, man, these guys really go to town with it on the science behind it. So here's a good one. They're looking at just the connection point there. So you can see here where the white arrow is pointing to all of this material transfer from the electrical conduction. And you can see on the good one, you don't have all of that material transfer and stuff. You just have this right here, just that very little bit where it makes contact. So then under the digital microscope, they showed you, see, here's that top view of the clip again with the hole in it. So remember, the tool makes the whole clamp slide this way down so that this giant hole right here, the square hole, will slide down and the wire is supposed to go here in it and stay pinched in there. But instead, the wire pumped up, the clip goes snapping back, and now you have arcing over the top of the clip, the spring clamp. And so there's a close-up view of the arcing. So yeah, that was pretty serious stuff going on there. Okay, so here's what ended up happening on wire 1. So you can see how this one edge here has a bunch of scratches here. So it looks like it had been sitting there at some point in time and getting closer and closer and closer to the edge of the opening on the top of the face clip. And each time it moved down and it dug in and dug in and dug in until it finally gave way. And then you're going to see the arcing here in a minute. There's already, like, I don't know if that's corrosion or just material transfer there from the arcing. See, and here they zoomed into it so you could see it a lot closer. So you're really only supposed to have just the one depression from the very first time that they insert it. And so they photographed it from all the different sides, and you can see just lots of amounts of material transfer and smeared material, all of that from electrical conduction. And this is what a good one should look like. This is what it looked like on the opposite side of it. See, just the one gouge line here and then these 2 points. That's what it should have looked like. And then this one I can't figure out because, see, here's what wire 3 looks like. He looks fine. That's an edge-on view of the ferrule with the wires. But look at wire 1, though. This thing's all bent out of shape and everything. So I'm willing to bet that when they assembled the ship, when they were building Dali and they first had this issue, I bet they tried jamming it into the hole and it just wouldn't go in there and it just kind of deformed. So that's what it looks like to me. And here's the other side of it. So just deformities everywhere on here, and just, yeah. See, so you have these linear gouges going this way. So this is why I think they tried forcing it in there. Totally bad. You can see where the arcing had taken place here. So these two pictures here show you what it should have looked like and what it did look like. So right here, wire 3 on that same terminal block, you can see how it came down into the hole in the terminal block. And they've removed the cage here so that you can see the ferrule, because you can see how far the ferrule is supposed to come down below the opening there. And then, but look at where wire 1 did. See? But look at what wire 1 did. See, it barely came into the cage. He's supposed to be all the way down here. And in the final case, this is what it's really supposed to look like. See, the ferrule is supposed to make it all the way down to the very bottom. And here you can see wire 1 was just maybe 1/3 the way down at the most. And so when they showed you the picture here of it zoomed in, this is the crux of the problem right here. Because you can see wire 3 is textbook, and it has that blue plastic collar on there that fits perfectly into the terminal opening so that the ferrule can drop all the way down. You see that? But look at this, wire 1, which is port number 381, he's not making it in because you could see the diameter of that label on there is too thick, and it won't allow it to go further enough down into the hole to make it all the way down to the bottom. So this was it right here, folks. This little piece of plastic right here caused 6 people to lose their lives, and it caused hundreds of millions of dollars, and it caused many people to lose work for several weeks, and it just caused just incredible amounts of damage. And who would have thought that a little cheap part like this could be the root cause to such a massive amount of destruction? By the way, if you haven't seen my video on the NTSB's final report on the OceanGate Titan submersible implosion, check this video out right over here. And if you didn't see my other video update on the NTSB's preliminary report on the UPS plane crash up in Louisville, Kentucky, check out this video right down here. Well, thank you so much for joining us, and we'll see all of you on the next one.